Prove that for all n natural numbers, so that's our counting numbers, 1, 2, 3, 4, etc., that n squared plus 2 is not divisible by 4. Okay, well, the classic way of dealing with this question is to split it into two different cases. N is even and n is odd. So let's look at n as even. I'm going to let n equal 2 times p, where p is also a natural number, but it will guarantee that n is now even because it's a multiple of 2. And therefore, n squared plus 2 will be, or technically be identical to 2p squared plus 2, which is 4p squared plus 2, which is actually 2 more than a multiple of 4. We're just going to add so not divisible by 4. Then for n odds, they're going to be very similar, but let's n equal 2p plus 1. That will guarantee it's an odd number because 2p is even, and then adding 1 onto it. P can then be any natural number. Remember, this is so important to do. You can't just try out some different values of n. We're proving it for any value of n, given it's a natural number. Okay, because p can vary 1, 2, 3, 4, 5, and so on. So now it's a little bit more complicated. We're going to get, oh, hold on, let me write down, n squared plus 2 is going to be 2p plus 1 squared plus 2, which will give me, this is a double bracket, so 4p squared plus 4p, because I get a 2p and another 2p, plus 1 plus 2, which can be written as 4p squared plus p. I've factorized out the 4, and I'm left with 3. And this is 3 more than a multiple of 4. So also not divisible by 4. And I'm just going to conclude, like say, proof complete, because I've looked at both cases, shown that it's not true, so overall it also cannot be true. Let's take a look at the second part. Given x is a real number, the value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. State, giving a reason, if the above statement is always true, sometimes true, or never true. Now, you might be tempted to just try some values out here, and it is a good way to go, but I'm going to show you a slightly more advanced way, and that is to sketch the graph of y equals the modulus and y equals x minus 9. Let's start with y equals x minus 9. It's got a gradient of 1, a y-intercept of minus 9, so it's going to look something like that. Just going to do it in a different color, I think. And let me do the other one in red. So good to learn how to plot modulus functions. We just need to find the critical value for where this becomes 0, and that's going to be when 3x is equal to 28, so when x is 28 over 3. Actually, that is 9 and a third, so it's just a little bit to the right of 9. I should have added, actually, this is minus 9, and then this is going to be 9. So when x is 9 here, we're going to get 0. And now I've got a steeper gradient. It's going to look a little bit like this. Okay, it's going to be 28 at the top. That's not that important. But what we can see is that there is a region where the blue line is above, so where x minus 9 is greater, and there's obviously a region where the red line is above, which means that it's sometimes going to be true. So 3x minus 28 is sometimes above x minus 9, and sometimes below. Therefore, a statement is sometimes true. I think that's a pretty comprehensive answer, to be honest. looking from the graph, we can see this little region. Now, your alternative is to try some values. So you could maybe try x equals 0, then the modulus of 3x minus 28 is going to be 28, and x minus 9 is going to equal minus 9. And we can say in this instance that the modulus is going to be greater than x minus 9 when x equals 0. If you just try lots of other values, you're going to find it's greater for most of them. For example, when x is big and positive or big and negative, you're going to have to actually look at this region here, and it might, you need to look at the critical value really. So x is equal to 28 over 3, then 3x minus 28 would actually equal 0. X minus 9 would then equal a third. So x minus 9 greater than modulus 3x when x equals 28 over 3, and therefore statement sometimes true. It's just an alternative if you're not so happy with drawing the graphs, but what I would say is practice them because it comes in really useful when you're solving modulus equations. But those are two different approaches. Well done.